Welcome back to the deep dive. Today, we're plunging way back into the fossil record.
That's right. We're looking at Ichthyosauria.
The fish lizards. These incredible marine reptiles, they basically ruled the oceans for, over 160 million years?
Yeah, throughout most of the Mesozoic era, starting around 250 million years ago, give or take.
Right up until about 90 million years ago.
A huge chunk of time.
And our mission, really, is to get our heads around this massive shift. How did land reptiles, we don't even know exactly which ones, commit so fully to the sea?
And not just survive, but thrive, become apex predators.
Okay, let's unpack this story. It's quite something.
Well, the first thing that jumps out is just how fast they seem to have perfected that aquatic life. Ichthyosaurs are maybe one of the best examples we have of convergent evolution.
Convergent evolution?
Yeah.
So looking like something else, even though they aren't closely related.
Exactly. Think dolphins or, fast fish like tuna. Ichthyosaurs developed incredibly similar body shapes.
Streamlined bodies, you mean?
Right. Streamlined, often a dorsal fin, stiff bodies, and that vertical tail fluke, all for efficient swimming. Millions of years before whales or dolphins even existed.
And their anatomy really backed that up, didn't it? Highly specialized.
Totally. Those limbs, they weren't feet anymore, fully converted into flippers.
More for steering than propulsion, I gather.
Primarily, yes. Especially in the later, more derived forms. The power came from the trunk and, crucially, that tail.
That vertical tail fin you mentioned, driving them like a tuna.
Pretty much, yeah. That's what we call thunniform movement.
Yeah.
It's all about maximizing thrust from the tail while keeping the body rigid, built for speed.
Speed for chasing fast prey, presumably.
Absolutely. And if you're hunting fast prey, maybe in deeper, darker water, well, you need good senses.
Which brings us to the eyes. I read they were enormous.
Record-breakingly enormous. The largest eyes of any known vertebrate relative to body size, or even in absolute terms for some species.
Wow. And they had protection, too.
Yes, large bony rings inside the eye socket. Scleral rings.
Like internal goggles?
That's a great way to think about it, yeah. Probably to handle the immense pressure at depth, projecting the lens.
Pressure. So how deep are we talking? I saw estimates for Temnodontosaurus, like 1,600 meters.
The calculations suggest it's plausible, yes. That's over 5,000 feet down. Incredibly deep. It paints a picture of a very capable deep-diving predator.
A biological submarine, essentially. But wait, diving deep, swimming fast in potentially cold water, that takes serious energy. Reptiles today are mostly cold-blooded. How did they manage?
Well, that's where things get really, really interesting. They weren't like modern reptiles in that respect. Not at all.
So they weren't sluggish. They had some kind of internal engine.
We have pretty definitive proof now, locked in the chemistry of their bones and teeth. Isotope analysis.
Okay, what does the chemistry tell us?
It tells us they were warm-blooded. Homeothermic endotherms is the technical term.
Warm-blooded reptiles.
Yep. Their body temperature seems to have been consistently high, around 35 to 39 degrees Celsius, significantly warmer than the surrounding ocean.
That's a game changer. So they could hunt actively anytime, anywhere.
Basically, yes. And they likely maintained this with a high metabolism and, crucially, a layer of blubber for insulation, just like whales and dolphins today.
Blubber. We know they had blubber.
We do. Thanks to some exceptionally preserved fossils, particularly from Germany, you can actually see the body outline, the fins, even traces of skin, and that insulating layer.
Incredible. Okay, so warm-blooded, insulated, deep diving, that high metabolism must have implications for reproduction too, right? They couldn't haul out on beaches to lay eggs like turtles.
Exactly. Too specialized, too committed to the water. And again, the fossil record provides the answer, viviparity.
Live birth at sea.
Correct.
Yeah.
We have fossils, again from Holzmaden in Germany, showing mothers with embryos or newborns still inside the body cavity. Undeniable proof.
Wow. And wasn't there something odd about the birth orientation?
Yes, it's a fascinating detail.
Yeah.
The really early, more basal ichthyosaurs seem to have been born head first, like land reptiles.
Which sounds risky underwater.
Very. The baby would need to get to the surface fast. But the later, more advanced forms show tail-first birth.
Just like modern whales and dolphins.
Precisely. It dramatically reduces the risk of drowning during birth. Another example of them perfecting aquatic life.
It's amazing how much we've pieced together. And we should probably mention how this all started, the discovery. Mary Anning, right?
Absolutely. Her and her brother Joseph, down in Lyme Regis, England. People had found bits and pieces before, but their discovery of the first complete skull in 1811 really kicked things off.
That really launched serious study, didn't it? leading to the formal naming of Ichthyosauria a couple of decades later.
It opened the world's eyes to these incredible ancient sea dragons.
So, summing up, we've got these highly advanced, warm-blooded, live-bearing marine reptiles. True apex predators ruling the seas for, well, an immense stretch of time.
Masters of the ocean.
Yeah.
Who vanished. Around 90 million years ago, significantly before the big asteroid impact that wiped out the non-avian dinosaurs.
So it wasn't the KT extinction event. What happened then?
It seems to have been more of a slow decline, a two-step process, maybe, linked to major environmental changes in the early part of the late Cretaceous.
Climate change, sea level fluctuations.
Things like that, yes. Ocean chemistry changes, possibly disruptions to their food webs, maybe increased competition from new types of large sharks appearing then. It looks like environmental volatility hit them hard.
Their world changed, and maybe their specialized way of life just couldn't adapt quickly enough this time.
That seems to be the most likely scenario. They were incredibly successful, but perhaps too specialized for the world that emerged then.
Which leaves us with a final thought for you, our listener. Considering just how dominant and biologically sophisticated these ichthyosaurs were, what pressure or combination of pressures could ultimately overcome a lineage so perfectly engineered, seemingly, for the open ocean?
And perhaps are there lessons there about the vulnerability of highly specialized species in our oceans today facing their own environmental changes?
Something to ponder. That's all for this deep dive. Join us next time.